Okay, today we're going to discuss everything that man knows about science, the universe, and time, and all that good stuff. And we're going to start with the creation of the universe according to what I've known and what I've learned over the years in studying science. We're going to start up in this corner over here. Okay. So the very first thing that we know was created in the universe was a positive charge and a negative charge. And we know the positive charge and the negative charge has no mass unless there's movement or energy to make this mass take place. Mass is energy, and energy is mass, according to Einstein's theory, and they proved this a couple of years ago in France. I believe it was France. It was a European physicists that took a non-particle and increased it, accelerated it until it had weight and mass, and they could actually measure the mass of it. So we know that subatomic particles, when they're accelerated, gain in mass. And so we also know that as they accelerate and they speed up, they gain in more mass. And they continue to gain in mass as long as they're accelerated even faster and faster and faster. There's more mass involved in the acceleration. So what happens is, this is the guess, they don't know for sure, but the electrons are spinning around the outside of a neutron. Electron, and this is the proton, and the center. And this happens to be the very first element that was ever put into existence, and it's called hydrogen. And hydrogen has a molecular weight of 1. Oddly enough, it's got 1 electron and 1 proton, so it has a molecular weight of 1. So what happened is that there was a huge mass of this matter that was brought into existence. And when it was brought into existence, this great big huge cloud of matter started to clump together. All of this cloud, this huge cloud of electrons and protons that created the first element of hydrogen, clumped together in the center of this spot in space. And it became very, 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 very compacted, very small. And all of the matter and energy and everything that we see today was put together, and it's one huge clump. For lack of, it's like it was drawn together by something. And it became a very, very small object in space, relatively speaking. And because it was small and it contained this tremendous amount of these electrons and protons and these very first primitive elements called hydrogen, the actual elements of the entire universe were created that we know they're stable. So what happened is they compressed, and through nuclear fusion, inside of this fusion reactor, for lack of a better term, there was a adding. It would add an electron, add a proton, add another electron, have another circle around there, electrons were added, more protons added, an electron was stuck in here with a proton, and it became what's called a neutron. Because there is no such thing as a neutron, it's only a particle that is neutralized because it's 1 plus and 1 minus collected together in one space. And it has tremendous mass, by the way, when it does that. So eventually all the elements in the periodic table of the elements was put together in the basic levels, except for the radioactive ones, which were created on the Earth. So what happened is this thing just collected and collected and collected and just kept fusing all of these electrons and protons together that were circulating around each other. And at this time, the speed that these were operating at was slower. It was slower so that just under this pressure alone, this could happen. This could be created. Then as soon as it was created, it was brought into a very small, tight space that nobody knows the size of it. Some people say it's the size of a pinhead. People say it's the size of a baseball. Some people say it's the size of a huge sun. But nobody knows, because this matter was actually energy that was compressed to a point of fusion. And then what happened is it exploded. And it exploded and went out in space in all directions, all directions, all directions. And how we know this is happening is because you can see that the universe is accelerating, it's spreading out in all directions from one point in space. We can see that using telescopes and timing, using Doppler effect, and seeing that it's moving on. Okay? But it's also doing another thing that we discovered. It's accelerating. The speed at which it's expanding is also accelerating. Okay? So we know that energy, when you accelerate energy, it becomes mass. And when you take mass and you blow it all apart, it's nothing but raw energy. This was Einstein's theory. So what we've got going on is these elements are actually pure raw energy that become the visible world that we see and creates mass, density, all the elements that we see. And so what happens is that scientists have discovered also that the universe is accelerating. They know it's accelerating because by using a Doppler effect of the light frequencies of these planets moving away from us, they can see that they're having a shift of increasing or changing their color hue as they get farther away from the central space. So we know it's not only is it expanding in all directions, it's also accelerating. Okay? So we know that when energy is accelerated, it becomes much more dense. In other words, the faster you move the particle, the more dense it is. Those physicists in Europe, when they sped up the subatomic particle and sped it up to a very high speed, it became dense, it became visible, it had weight. What that means is that in the process, it became matter. In becoming matter, it became more dense. That means the more it was accelerated, the more dense it becomes. So as you expand that out, the more something is accelerated, the denser it becomes. The more compressed, the more slower the reactions are of the individual pieces. So we know that what's happening is that if this started out, it had to start out at a very slow speed, otherwise the fusion could not take place. If it was doing a very rapid speed and extremely hard and was very dense, then these dense hydrogen atoms would not fuse. They could not fuse if they were extremely dense. If this was speeding up so fast that the density was so high, then nothing could penetrate, nothing could join, nothing could break apart. So we know that in the beginning, all of the atoms, the electrons were traveling at a much slower speed, just barely enough speed to create the very first inkling of matter. And that was this gas called hydrogen. So now we know that the universe is not only is expanding, but it's also accelerating. So what that means is that mass is becoming more dense as time goes on. As the future goes on, the world and everything around it is becoming faster and faster and faster and faster and faster, and there is no limit to the speed at which this energy can travel to form matter. There is no limit. What we see in the universe is the speed of light. We think that's the limit of the speed of the universe. That's not even a plausibility. All we know is that the speed of light is the fastest thing we've ever been able to measure, but that's not a limit. There are no limits in the universe. So we know that this is speeding up, and as it speeds up, this is speeding up, and as it speeds up, and guess what time is? Time is a measurement of mass and energy. Okay? If mass and energy is also accelerating, then time is also accelerating. And it's accelerating at the same speed that the mass and energy is accelerating. So time is relative to the moment in time and space where you exist, and relative to the motion of the atoms and the decay and the speed at which the planets are moving around the sun, and the Earth is rotating on its axis, which is constantly speeding up, even though you have no clue that it's happening. So now the question is, how old is the universe? If we started out with a very slow acceleration at the point of the Big Bang, the first explosion of this, that means that we are constantly accelerating in both time, and we're increasing in density of mass as we expand out from the central point in space. So the only thing that's constant in the universe is change. Time is not a constant. It can never be a constant if it's based upon matter, which is constantly expanding and accelerating and gaining in density. So in the very beginning of the very first of these radioactive pieces of matter that mankind uses in order to date material with, you have I call it the parent material, which is a radioactive isotope that actually, this would be like uranium, okay? And uranium is created in volcanoes. It's actually a fusion that takes place on Earth. And because it's a non-stable radioactive material, it can never last out in space for very long. So it can never travel as far as it traveled to get to where the Earth is today as the original matter. So it has to be recreated. So it's recreated inside of volcanoes and the Earth, down here under extreme pressure and heat. Pressure and heat, and it comes up and it escapes the volcano, comes down, and you find uranium coming out of the volcano that's created at the time that the volcano erupts. So the theory is that the radioactive material decays at a constant rate. And the reason why they think it decays at a constant rate is because they're living in this time zone, this time speed continuum, and they can only see the decay rate of this matter under this time and this situation. Everything is relative to science based upon the conditions of the time that you're measuring, doing the scientific experiment. If the conditions change, then the experiment changes. We know that there's certain laws of physics that kind of work, but they only work within our time and space continuum that we're in now. So what's happening is time is accelerating because guess what? The universe is accelerating. Because time is based upon mass and the movements of energy. So we know that these electrons are also accelerating because everything in the universe is tied together. Nothing is not tied together. Everything is tied together as a one piece because they all started from one place, one spot in the universe, and they all were all started with this concept of energy in motion creates matter. So as it accelerates over periods of time, over vast periods of time, the rate at which this decays is constantly changing because the density of the matter is constantly changing because the speed at which the electrons are moving around this nucleus is changing drastically over time. Now, in order to determine how old the universe really is, you have to come up with a way of measuring this acceleration of time and energy creating mass and density to determine how much density is being increased every year as we exist on this planet based upon our time-space continuum. That means that it's a curve of constant change and constant flux, and it has several factors in it. Time is a constant variable that's measured by energy, and the energy is constantly accelerating. I don't have the formula for this yet, but I'm working on it. But here's the factors. We know that the universe is accelerating from this point to this point. We can see it by measuring the speed at which the planets are moving away from one point in space and how they're accelerating. If we can pinpoint this over a period of, say, 50 years or so, we should be able to come up with a rate of speed that it's accelerating. The problem is the rate of speed is accelerating in this 50 years here this is 50 years, is going to be different than the rate of speed it accelerates in this 50 years. And the 50 years is also changing its time continuum. So we have to come up with a formula to determine what that time continuum is in terms of time as it is today. If energy is accelerating, speeding up and becoming more dense, and time is getting shorter and shorter because of this speeding up, and mass is getting more dense and dense, that means that the time that it takes for this radioactive material like uranium to decay has slowed down drastically over the period of time from the time it was first created, well, millions or billions or quadrillions of years ago, because nobody has a clue how old the universe is, because they're using a linear time frame. They think it's 3.4 billion years old because this matter decays at a constant rate in our time frame. However, our time frame is not realistic because time is constantly changing, because time is based upon the fact that energy, matter, and motion creates time. So if energy and matter and motion creates time, and the energy and matter is constantly accelerating and speeding up, then that means that the time it took for this radioactive isotope to completely turn into lead has greatly slowed down as the world has gone on in time and space. And what clued me into this was, if it takes so many billions of years for this particular uranium to turn into lead, and that time is greater than the Earth has been in existence according to their dating scheme, how is it that there's pure lead on this Earth with almost no uranium there in the same area? It's impossible for pure lead to exist on this planet, any place, without a high concentration of the original isotope of uranium. Impossible. So that means that if uranium is the only source of lead, which you have to believe it is because that's the only way we've ever seen it, that means that uranium used to decay at a much, much higher rate and turn into lead much, much faster than it does today. So the formula for this is going to be relating to how fast we're accelerating here based upon a time frame, how fast we're accelerating based upon a time frame, and you have to accelerate the time frame also because the time is getting shorter and shorter and shorter and shorter. 50 years is now becoming a blip. Time is becoming shorter because the universe is accelerating. Time is measured by the movement of energy. Everything in the universe is accelerating, going faster and faster and faster and faster and faster, becoming more and more dense, losing more and more ability for it to decay as fast as it used to. So the rate of decay that we have now between uranium and the lead, or any of the radiometric dating methods, is completely with unfounded data. It's based upon a little pea-brain idea that the universe is constant, time is constant, and we're not taking into account the fact that matter is accelerating and mass is constantly becoming more dense. The faster you move this energy, the more dense it becomes. The more difficult it becomes for it to break down, the slower it breaks down. Period. The formula for this is going to be based upon the factors of measuring time and space, going out in space, measuring time and space, measuring acceleration of this, interpolating as much as you can, and realizing that 50 years here might be 49 years what it was 20 years ago. And then 50 years on farther in space might be 25 years that it was back in the 1950s. And if you keep going and it's keeping accelerating, that means that it's getting shorter and shorter and shorter and shorter and shorter, so that by the time we reach the point where this is supposedly the expansion is going to stop, and it can no longer go any farther because the mass is so dense it cannot expand anymore, it's going to slow down and swing back supposedly like a pendulum, and collapse upon itself. But before it does that, the time gets shorter, shorter, because we have nothing but acceleration at this moment of energy and time and space. So in order to determine this, we have to look at several markers. And we have to have markers that have enough time and space in between them to where we can interpolate. We keep going on. By the time we get down to, 40,000 years ago, or whatever it is, whatever the time we come down, whatever we figure when we start calculating this back down, we'll come back down to the point in time and space where the universe actually did start, because we can see by the amount of acceleration at what point in time and space it did start, because it's not linear. It did not start in a linear fashion, and all the energy that we have today is accelerating. You cannot see it accelerating because guess what? You're in this time and space here. You have this little tiny little minuscule peak at the universe. Your time and space that you are experiencing right now is your time and space. Everybody that's in this time and space is experiencing the same time and space. Everybody that was here 100 years ago was experiencing a different time and space. Everybody was here 10,000 years ago, if they were here then, is experiencing a different time and space. Time and space are not consistent. They are only thing that's constant in this universe is constant change. Nothing remains exactly the same. Every molecule that you're looking at that we see today was at one time was much less dense. Everything was much less dense. It's getting more and more dense as it speeds up. That means that the rate of decay is slowing down on all this matter. The time that this takes relative to now is same relative to then, but much, much faster relative to now. I hope I haven't blown your mind too much with this, but all of this started about 2 years ago when they took matter and they accelerated it. And you know that in the process of accelerating, not matter, energy, to make it into matter, that at some point it started to become matter. Then it became more dense. As they kept on accelerating it, it became more dense. So we know that the universe is accelerating all the time, so we know that matter is getting more and more dense as it speeds up, as it accelerates. And the entire universe is tied together to the same time speed thing, where everything is accelerating at the same time or it would collapse on itself. If everything was not accelerating at the same moment, same way, then the whole thing would collapse on itself, because every part of it has to work on the same time-space continuum or it all collapses on itself. So if this is accelerating, these electrons are accelerating. If they're accelerating, that means that this is becoming more dense. The matter of the electrons is denser than it was 10,000 years ago, 100,000, a million years ago. However far back you can go, this was a much lighter material that was able to decay much faster. There you have it.